In this work, we present a novel HDR deghosting method for processing very high resolution images. The image resolution has increased dramatically over the years. However, the existing HDR deghosting methods can only handle up to maximum of 5 megapixel in a standard 12 GB GPU. In particular, the current state-of-the-art method can process 2 megapixel in 12 and 3 megapixel with 20 GB memory, and it requires more than 20 GB GPU memory to process full HD images. Comparatively, our proposed approach can process up to 16 megapixel images with just 12 GB memory. The existing HDR deghosting methods are not scalable to process full HD images. Hence, our goal is to propose a deghosting method that can process full HD images without compromising on the quality. The main reason for this drawback in existing methods is that they process input images at full resolution with the CNN. Thus, the bottleneck is to use a bigger GPU for a very high resolution images. In our proposed approach, we process low resolution images with the CNN and upscale the result to full resolution using bilateral guided upsampler. However, the BGU model requires a structural guide image to predict the upsample result. Such a guide image should be a high resolution fused image without any ghosting artifacts. To generate the guide image, we train a CNN to predict low resolution weight maps. Then, we upscale it to full resolution using bicubic interpolation. The upscaled weight maps are used for merging input images and obtain guide image. The guide image is generated in two steps: motion compensation followed by the weight map based fusion. In the first step, low resolution inputs are passed to a CNN network NMC to segment moving regions between the reference and other non-reference images. We use UNIT model with skip connections for NMC. The output of NMC is a low resolution binary segmentation map with 0 indicating the absence of a motion at that pixel in either reference or the non-reference image, and 1 indicating otherwise. Using the predicted motion segmentation maps, we perform motion compensation in the input sequence. The motion compensation is achieved by replacing the moving regions in the non-reference image with the regions from the reference image at the same location. Naively fusing high-resolution motion compensated images using classical fusion methods like triangle function may have artifacts in the guide image. Hence, we correct such artifacts using a trainable CNN NNG. With low-resolution motion-corrected images as input, NNG generates 3 weight maps, one for 3 input images. The weighted sum of upscaled weight maps and high-resolution motion-compensated images results in a high-resolution guide image. It should be noted that throughout this process, both the inputs and the predictions of NMC and NG are in low resolution. Though the guide image does not contain any ghosting artifacts, it suffers from a no HDR content in the moving regions. As pointed out by the red arrows, the saturated moving regions does not have HDR content in the HG, while the final result can hallucinate those details clearly. Once the guide image is ready, we use it to predict the final HDR image. In this stage, the low resolution input images are aligned using optical flow to compensate for camera and object motion. 3 aligned input images are passed to a 3-layer encoder to extract individual image features. The extracted features of reference and non-reference image is concatenated together and further processed by another convolution layer. By doing so, the network has the ability to compare both feature maps and choose the properly exposed details from both. This operation is repeated for all 3 convolution levels of the encoder to produce final feature maps for non-reference images. Then, the reference image feature is concatenated with the 2 other final feature maps of non-reference images. The concatenated feature maps are further processed by 3 extended stacked and dilated convolution blocks. A higher receptive field is necessary for the network to faithfully reconstruct uploaded and saturated regions. We achieve that by using XSCC block. The XSCC block has 3 stacks of 3 convolution layers with a dilation rate of 1, 2, and 4 and the kernel size of 3 by 3. The output low resolution feature map of final XSCC block is passed to the BGU, which takes high resolution guide image to predict the final fused HDR image in the high resolution. The loss for training the entire model consists of 3 individual losses at each subnetwork. To train the segmentation network, we compute the binary cross entropy loss between predicted and the ground truth segmentation maps. The L2 loss between the guide HDR and the ground truth HDR is used to train the NG model. Here, the T function denotes the mu law tone mapping applied on HDR images before computing the loss. Similarly, the L2 loss between the final image and the ground truth HDR is used to train NF model. The total loss is taken as a weighted sum of 3 individual losses, where alpha 1, alpha 2, and alpha 3 denotes the weight value assigned to individual loss functions. We assign low value of 1 e power minus 4 for alpha 2 and alpha 3 for initial 25 epochs, thus making the NMC node model learn better segmentation maps that could improve NMG. From 26th epoch till 50th, we set alpha 2 to 1, and for epochs after 75, all 3 weights are assigned to 1. We trained our model on a dataset provided by Kalantari et al. It consists of 74 training and 15 testing images with the ground truth. Additionally, we also tested our model on other publicly available datasets as well. For training NMC model, we have generated a ground truth by annotating the moving objects in each input image. For a sequence with 3 images, we generated 3 segmentation maps by manually annotating only the moving regions. The ground truth is obtained by taking the union of 3 reference and non-reference image segmentation masks. In total, we have annotated 89 images of UCSD dataset. We compare our proposed method against 7 existing methods in 2 publicly available datasets using 3 full reference image quality assessment metrics. We observe that our proposed method with BGU for downsampling factor of 8 performs better than almost all methods in both datasets. Additionally, we present results for another variation of our model without using BGU. From the results reported in the table, we see that the network trained with D is equals to 1 shows better performance than all other methods in all 3 metrics for both datasets. In the leftmost graph, we compare the running times of 7 methods for different resolutions from 1 to 16 megapixel. The non-deep methods by Sen et al. And Hu et al. Takes up to 468 seconds and 893 seconds respectively to fuse a 4 megapixel sequence. Among the deep learning based methods, Wu et al. Method takes up to 10 seconds to process 1 megapixel image and can only support up to 5 megapixel. Comparatively, our proposed method with the D is equals to 8 can fuse 16 megapixel images in 11 seconds on 11 GB GPU. In the second graph, we report the average PSNRT score for 15 test images of size 1.5 megapixel from the dataset of Kalantri et al. In the rice mode graph, we show the performance of our proposed approach on various downsampling factors. While D is equals to 1 method achieves the best performance, the time taken for processing in full resolution is in the range of 54 seconds for 1.5 megapixel resolution. Comparatively, downsampling by a factor of 8 has equal balance between speed and accuracy. In the first table, we present the ablation on different ways to supplement or generate guide image. We observe that while the individual performance of NMC and NG is low, using them together can result in significant boost in PSNR. In the second table, we present the accuracy obtained with the different types of inputs to the fusion model. The low score for passing input images without optical flow correction is because of the fact that NF has to perform both motion correction as well as fusion. In the third table, we show results for different choices of network architecture. The vanilla network denotes using 10 convolution layers instead of XSSE block. In this example, we show the ground truth and the predicted motion segmentation maps and the motion compensated LE and HE images. In the zoomed regions, we see that the motion compensated images still have artifacts that are corrected in the guide image. Here, we show 3 varying exposure input images from the UCSC dataset with the middle one as a reference. Notice that this sequence has a large focal motion. And this is the corresponding HDR generated by our proposed approach. Existing methods introduce structural distortions for moving objects in saturated regions and hallucinate details in heavily saturated regions. Comparatively, our proposed method generates visually pleasing results without any artifacts. This is another challenging sequence from UCSC dataset with heavily saturated moving regions in the reference image. Our model can predict high-quality ghosting-free HDR images even for challenging sequences. The zoomed regions highlight the artifacts by existing methods in reference saturated moving regions. Here, we show another zoomed portion highlighting artifacts by existing methods. This is another sequence from Sen et al. Dataset with camera and object motion. These are the results by proposed method and the Kalantri et al. Method. The results by Kalantri et al. Method has hallucinated new details in the cloud region, whereas proposed method is void of any such artifacts. In summary, we have presented a novel HDR deghosting method that can improve the state of the art in generating high-quality artifact-free HDR images. Our approach can fuse 16 megapixel images in just about 10 seconds on a GPU with 11 GB memory and achieve state-of-the-art results in publicly available datasets. Additionally, we present annotated motion segmentation maps for the UCC dataset. We have also demonstrated the use of BGU for tasks where guide image is not readily available. We hope that our paper will motivate the research community to explore BGU for the further fusion tasks. Thank you.